Welcome to the sneak peek of modeling physics instruction. This is a sneak peek of kinematics, which is the first modeling workshop that most physics teachers attend. And I'm Colleen, and there's Larry there with the periodic table of elements behind him. And we're really old modelers. We've been modeling for a pretty long time, and we've been leading workshops for a pretty long time. And when we heard that we needed a mechanics sneak peek, we just said, oh, let's do that. Let's just do that for old time's sake.
That's right. It'll be fun.
Yeah, it would
Down
be
memory
fun.
lane.
So I'm an old physics teacher from way back who, went back to school and got a PhD in physics education research. But I still, teaching is still the most fun I've ever been paid to have. And so any chance I could get to hang around with high school teachers, it just takes me back. Makes me feel relevant again. And Larry?
Exactly. And I'm probably one of the original modelers, started in 1990 and led my first workshop in 1995 in mechanics. And basically, I've been running workshops here and there in physics and chemistry since then. So,
And he wrote the chemistry materials.
yes.
He's too modest to mention that, but I'll mention it for him. All right, so that's us. We're here to provide you with a taste of modeling and modeling instruction, and what it would be like to take a mechanics workshop if you've never done that before. So let's just start right in. We're gonna do modeling. It's great to talk about stuff, but it's more relevant if you actually just do it. So if you would, please put on your student hat. I'm putting on my student hat. Every modeling unit begins with a lab. So we're going to begin with a lab, and we have a video for you to watch. And so you're going to watch that video and think about what you're seeing, and then we're going to talk about it. All right, imagine that. What could it be? So, what did you observe?
Ellen, give you a chance to go first.
Well, my students usually say the buggy moves at a constant speed.
Do they really?
Yeah.
Mine used to say, oh, it's red.
Yeah, that's right.
It's a red toy. It's battery powered.
Lights
What
are
else?
blinking.
Ray, what do you see?
Yeah, it's a self-propelled car going across the floor.
It is. It's what else? What else?
Battery
We're gonna
powered.
look at it again just because, you can never have too many moments of tumblebugging.
Moves in a straight line.
It does move in a straight line, and if you're looking really close, you can see something happening at the rear of the buggy. I'm going to just do that again. Oh, it's really subtle. Maybe you have to know what to look for. Notice anything, Sue?
It took about 10 seconds to get from start to where we could no longer see it.
It did. It did. And if I was in a classroom and I had a whiteboard, I would be writing all this stuff down that people are saying. What I was hoping you could see, but it was too subtle, was that there's a little flashing light on the back. Get this little blinky light on the back. Okay, so it's moving in a straight line. It's moving at a constant speed. That's what Alan said. It's moving at constant speed. How do you know, Alan? Do you
Just
have a
by
little built-in speedometer in your eyeballs?
No, just by looking at it.
just by looking at it. It looks like a constant speed, but that's something that needs to be measured, I think, to be sure. We would have to check that out before we can make that claim. So we'll just put that out there as sort of a pending claim. And if I wrote that on the board, I would say, oh, question mark after that, constant speed. Okay, I'm gonna just
Yeah.
write on this slide.
Yeah, and I guess what I would say, just qualitatively, it didn't seem to be speeding up or slowing down.
Anything else? Made a noise, right? Or did you hear that?
Hear the noise.
Made a noise. Blinky light. Red.
Red. I was going to say red.
Okay. Anything we want to add to that list? All right, we're gonna hold those thoughts, and now I'm gonna ask you, of the things you saw, are there any things that you saw, notice there that you could measure? Anything you could measure?
The time it took to cross the screen.
Yeah,
The distance it went before it stopped?
could measure the distance it traveled. What else?
How fast the light blinks.
Yeah. Oh,
Well, and I was wondering, can you measure? I was looking at as it went across the boards. How many boards did it, pass per every time it blinked?
Blink, what an interesting idea. Boards per blink. Could we measure that? We probably could. In fact, since it's a video, one of the things I think that we all learned to do during COVID was like do measuring in videos. So that is a possibility. But for the purpose of this webinar, I think we want to think of this as it actually happened in front of me in the room. I have all of us have a dune buggy, and we turned it on and it went. Because that's what happens in a classroom. So we're trying to channel, classroom as closely as possible. Okay, well then, keeping these things in mind, that these are measurables, let's then think about what relationship there might be between any of those quantities that we named on the last slide. Are any of them related to one another? Yes, Sue says yes. Which one, Sue?
Well, we talked about constant, it didn't slow down and it didn't speed up. So distance versus, we didn't use the word speed.
So when you're making measurements, and you want to make a whole bunch of measurements, what is the sort of the variable that you choose to guide you in making those measurements, or to the independent variable to use for making measurements?
Would it be time?
Would it be time? What do you think? What do you guys think? Could it be
I like
time?
distance versus. I like that. I like
Distance versus time? Okay. Are we all good with that? Alan, you like distance versus time?
Yeah.
Okay. Okay. So your mission, should you choose to accept it, whether you choose to accept it or not, your mission is going to be with your lab group. I'm going to put you in breakout rooms, and you must find the relationship between position and time and represent it in different ways on your whiteboard. We're going to use the built-in whiteboards that Zoom has. You will see on your Zoom controls at the bottom of your screen. If you put your cursor down there, you'll see that one of the options is whiteboard. So when you get into your breakout room, one of the people in your room should open a whiteboard so that you can all write on that. And before you leave your breakout room, anybody in the group, doesn't matter who, needs to take a screenshot of that whiteboard. And I have slides that you're going to put those screenshots on. So it looks like we're going to have two groups. And so group one is going to use whiteboard one, group one, and group two is going to use whiteboard group two. And I'm putting the URL for this set of slides into the chat. There. Has everybody got that URL?
Yes.
Any questions? I'm creating those breakout rooms, and then I will close them in 6 minutes. I'll make an announcement. You know, I'll send you a little message about a minute before I'm getting ready to close the rooms. All right.
And you're gonna
All right. Well, we've gotten a sneak peek at a couple of whiteboards here. Okay, so could you toggle between group two and group one?
Yep, I think so. There's group
Okay.
one.
So there's group two, there's group one. Okay, so what do you notice?
They look very similar. The graphs look very similar.
Graphs look similar? What is it about the graphs that look similar?
Well, looks like we have the distance certainly is increasing as time goes on.
Okay.
So how we arrive at whether, I guess it's distance from the starting point, right? So it's greater.
Okay, so it's distance from starting point and that increases, is that what you're saying?
And that's increasing, right? And it looks like the way they're similar is it looks like they go up by about, the same amount each time.
Uh-huh. Okay.
But it looks like just the way the represented is a little different, and I think it's because of the way the graph is built.
Uh-huh.
It
Okay.
looks
Okay, so could you toggle Larry to group two for a second?
Sure can.
Okay, so check that out. Is that telling us the same thing?
looks like it's telling us the same thing.
Yeah, but there's a one additional bit of information down there.
I noticed that we have a different variable on the vertical axis. We might want to talk about that.
You have
Well, we have distance and they have position.
did they say position? I thought they said distance.
No, here's
Nope.
group
Oh,
one.
It was
maybe.
position.
Oh, you say position. Oh, you're right. You do say position. Ray was saying distance, and I just, like
Never even looked at it. Yeah.
It's
I
okay, I'm just saying.
I did not store it in long-term memory. What can I say? But okay, distance, position. What's the difference? Are they the same thing?
They're both in meters, right?
They're both in meters. Okay, so you measure them with the same ruler.
Oh, shoot, I didn't even notice. You had the table, that was bad. The table had a header that said position. I should
Yes,
have,
it
Oh,
did.
sure.
you
it
should have
did.
used
Okay,
that.
so there was a clue for the person making the graph. Okay, so how far away from you am I, Sue? What do you think? Like 3,000 miles, 3,200 maybe? Okay,
Yeah.
so
Yeah.
distance is how far? Position. What's my position?
Position is where it is.
At 5808 13th Avenue, Sacramento, California, 95820 is my position. Okay, so I'm going to say maybe not quite the same thing. If you're talking about a distance and a position, this is a really important distinction in physics. And so we're going to talk more about that as the unit goes on, but we're going to put a pin on that for now. And I'm just going to say, I noticed one other thing about these graphs. They are similar, which is not surprising since you had the same data to graph and you had very little time, so you just didn't get done. But I notice on group two, you've just got a line on your whiteboard. And on group one, you actually plotted points and fitted a curve. And I really like that. Well done, group one. Well done. And the points didn't all just bam lie on the line, did they?
They did not.
They did not. They did not. Why do you suppose?
Well, I would think that, our measure, as we were measuring, it would be hard to kind of get that exact distance and exact time. So probably a little bit of variation in there.
Sure, a little measurement error. I think that makes a lot of sense. All right. Very good. Let's look one more time at group two's whiteboard. Thank you, Larry. And you notice at the bottom, underneath that graph, there's a teeny tiny mathematical expression. Let's talk about that for just a second. There's a number in there, 0.114, and there's another number in there, 0. And I'm going to say D. What does D represent in that equation? I think I know, but I'm just going to ask.
Well, you really should have made it position. But
Should have made a position. Okay,
Yeah.
but that's all right. You labeled your axis D and you have a D in your equation. So I think that's fair.
so it's the vertical axis variable.
Okay, the vertical axis variable is D. And then what about those two numbers that you've got? How did you get those? Or
Well-
theoretically, how would you have gotten them if I gave you more time?
Well, I was really lazy. I just noticed that it traveled, it was 1.14 meters away from the starting point in 10 seconds. And since it looked like it was kind of moving about the same, I just divided the 1.14 by 10 to get the change in position over the change in time.
And in fact, when you plotted those, if you had plotted those points like the other group did, you would see that that's a really good, that's a really close fit. If you had just drawn the line from 0 to 0.11 or to 1.14, that would have been a pretty darn good fit. Yep. So
Yeah,
I think in
we
this
didn't have a
case-
grid background, so we just sort of faked it, okay?
Yeah, I think in this case, you lucked out that your data was so good that it just fit that line perfectly. So the 0.114 meters per second, what does that mean? What is that on the graph? How does that relate to the graph?
What do you think, Sue?
The 0.114, it means something on this graph.
Meters per second.
Meters per second. So how would I find that on my graph?
I think if you went up that, was it 0.14
Yeah.
for every second, you're going to go up 0.14,
Okay.
right? So that would,
Rise over run.
right, yes.
Okay.
For every
Change in the position over the change in time?
Change in position per unit time. And then what about that last number, 0? It doesn't have any units, so I'm not sure what kind of 0 that might be. It looks like my only choices are distance and time. What is that 0?
Well, I stuck it in there because it looked like we started at 0 time, its position was 0. So that means that's just telling you that
Perfect.
that was its starting point.
It was a starting point. Excellent. Excellent. All right. So our equation is all those terms in our equation relate to the graph. And all of the graphical terms relate to the table, and everything's telling the same story on these two slides. So well done all. Larry, you can stop sharing now. We were gonna do, but we're kind of late. We've got a model now, right? We now have a model. This is a plot of that data that you had that Larry made for us in Vernier, and you can see, bam, that's beautiful. And if we fit a curve to it, look at that. It looks exactly like slide number 1 did, whiteboard number 1. So, and the key takeaways for the end of this whiteboard meeting would be that there's multiple representations that you can make of your measurements. And so that's what we do. We make and use multiple representations, and we coordinate those representations. So the slope of the line is the V in this equation, and the vertical intercept of the line is the X naught in this equation. And this is an equation of constant velocity. You did it. You built the constant velocity model. You guys are model masters. All right,
Sure.
we're gonna take that model out for a drive and see what we can do with it. Since we're a small group, I'm just gonna say, what do you think? What do you think you're seeing here?
So if we did that same car, except we didn't start at the 0 point, right?
This one like that?
Right. I'm thinking
Yeah.
that one above, right, that we would just start a little ahead and all the way along the line we'd be a little further along in distance,
Okay.
but the change would be the same.
Okay, so the rate of change, the slope,
Right.
is that what you're saying? Slope
Yep.
is the same.
Yep.
What does that mean about these two cars? If I had to like make that happen in a on my lab table, what would I be doing? Or on the floor?
One would start ahead of another.
Uh-huh.
But they would be moving at the same speed,
They'd be moving at the same speed or the same velocity.
same velocity.
All right. And what about this one? What are the blue and the red car doing here?
Well, it looks like the blue one starts well away from the origin,
Uh-huh.
And it's
but instead of going to the right or moving farther away, it looks like it's getting closer and closer to the origin as time.
Okay, so this guy, he's driving back toward the 0 point. And what about
So
this guy?
if the red line were going right, then the blue line, the car is going left.
Okay, so they would be, are these cars gonna meet?
if if
It-
if they were going along the same path in opposite directions, they would.
Yeah, it looks, well,
Yeah.
it sure looks like they're going, I mean, here's your, yeah.
But
What-
you could offset them and
Uh-huh.
get
Any idea where or when they would meet? Just from looking at this?
Looks like around 6
Five.
seconds
Shouldn't-
or
5 seconds.
5 seconds rather.
Yeah. 5-ish seconds and 0.6-ish meters. There it is. Bam, collision. Well, maybe one's floating above the other.
Or maybe they're side by side.
Or, yeah, they just pass each other like that.
Ah,
Okay, one more quick one. Two different buggies.
so they start the same place, just
Yep.
one is traveling faster than the other.
Okay, which one?
The yellow is
green
The
is-
yellow one is.
Yeah.
Sure.
How can you
guys
tell?
are- How can you tell?
I can tell because in the same amount of time, there's a more of a change on the y-axis. So I'm covering a greater distance in an equal amount of time.
All right. Very good. All right, that is a nice summary. And we are going to press on because time is pressing. Larry, over to you.
Slide number 13.
Yeah, I'm on slide 13. Can you see it?
I
You got
do.
the model so far.
So let's see let's make sure we got the points. We have a constant velocity model.
Yeah.
We haven't talked about a motion map yet, but I think we'll get a chance to see that if you look at the Unit 2 worksheet 4 key there. So if you were to click on that link, it'll bring up that document. And
So if we had worked our way through this unit, we would have gotten to those things. And so now we are most of the way through the unit and they meet this, where students meet this worksheet.
yeah, there's a few key points there. I think we make the point that the area under a velocity graph, notice that the velocity graph is a horizontal line because it's going at the same speed or all the way through, but the area under the line turns out to be the change in position. If you multiply, and if you scroll down a little bit, you'll see on the next page of that. Oh, it looks really, this looks really fine. It's hard for me to read.
Sorry, let me see if I can make it bigger.
There you go. There we are. That helps a lot with my eyes, aging eyes. Scroll up a little bit. And it says the area shaded is the displacement, which is the change in position. So you got 2 meters per second times 2 seconds. It comes out to be 4 meters, and that's what the area represents. And now we have a blue region over there, which tells you that the change in position is negative, which if you move the cursor over to the left to the position graph, you'll see that the change in position is from 5 seconds on down is going to be negative because it's going back towards the origin. Okay.
Yeah.
So these are the kinds of things that students work on to make sure that they understand and use the constant velocity model.
Okay,
Are we ready to?
ready to go back to the slides?
What we're going to do is we're going to look at something different. All right, we're going to look at a ball rolling downhill. And we're going to see, does our constant velocity model adequately describe this thing? And so I'm going to go. What do you think? Maybe let's look at it again.
Going really fast.
Yeah, not only is it going fast, but it appears to be
Picking up
speeding up as it
speed.
goes
Going
down. there.
faster at the end than in the beginning, yeah.
Right. And the problem is that whole thing, unlike the battery powered, the dune buggy, happens so fast, there's no way that we could mark the position of the golf ball like every 1 second or 2 seconds, because it only takes 2 or 3 seconds to get down to the bottom of the rails. So we have to modify our apparatus a little bit and see if we can try. We're going to try this device. So we have all right, we have this wheelie thing that has a little axle spindle, and it is rolling down in the space between the rails. And you will notice that it goes a whole lot slower than the golf ball, but you still see that it speeds up.
Mhm.
And you can, and we do, actually, somebody could call out every, say, 2 seconds, now, and somebody could put a mark on the rail, and then we could measure that change in position. We have a little meter stick there to show you how that could be done. And then that could be marked off. And so we have done that. And here is our graph of the position of the wheel on the rails.
By golly.
And I want to ask the question rather than tell you, how does this graph differ from any one of the buggies?
It's curved, not a straight line.
Okay,
A lot more dots.
what does that mean?
And I noticed at the end, there's for the same difference in time, there's a greater difference in distance covered.
Mm.
The main thing I noticed.
So
And the slope of the line changes. Like that curve is really made up of like the slope is flatter in the beginning and it becomes steeper at the end.
okay,
That's
so we aren't going to be able to fit a straight line to these data and have it work out very well. But there is a curve that you can fit called a quadratic, which shows that the position is equal to some constant A times, what's our variable on the horizontal axis? It's time squared.
Mhm.
Okay, so what can we do with that? Well,
Plug in numbers.
since we established that the slope of a position time graph, by the way, we use X for position when it's traveling in a horizontal direction. Since the slope represents the velocity, we can take the tangent to the curve at various points, measure the slope, and that will give us the velocity at that point in time. So at 10 seconds, this object was going 3.84 centimeters every second. Now, by using the tangents at different times, we can generate a velocity values. And what is the meaning of the slope of this graph? Well, look at the units here. We have 0.2351. That's centimeters per second. What does that mean?
That is a strange unit.
It is strange units.
It is. Seems like it's capturing how much it's speeding up,
Or
Okay, so
you know?
centimeters
Oh.
per second for every second.
Yeah, so yeah.
The
So
speed
for
in
every 1
centimeters per
second,
second.
it's gaining a 0.2351 centimeters per second every second.
So every
okay,
second that passes, it goes 0.235
Centimeters per
centimeters per
second.
second
Yes.
faster.
faster. All right, well, in the course of our classroom discussion, we would say this change in velocity for each unit of time is the acceleration. And that's so we can label this graph. The equation for this graph is the velocity at any instant is equal to the acceleration times the time plus the initial velocity. Now we're going to go back to the first graph. If you'll notice that the A term in front of the time squared is 0.124, and the slope of the velocity graph is just about twice as great as that number right there. We can say that the x position is equal to half of the acceleration times the time squared. Now, we're going really fast because we're pressed for time. This would take days in the classroom. But the point we're trying to make is that slope and intercept have physical meaning, and we can derive all of the standard equations found in all the intro physics texts using this analysis of the graphical behavior. Okay, ready to talk about what we mean by models, modeling, and modeling instruction? Why not?
Let's do it. Let's do it.
Okay, so David Hestenes, who's the father of modeling instruction, says that it's a conceptual representation of a real thing. So it's a representation of structure in a physical system or process. And we believe that there's a physical system out there that's capable of being examined. Each of us makes sense of it in our own mind by making a conceptual model. But my mind is different than Colleen's or Ray's. So what we have to agree upon is a set of symbolic representations to describe what's going on so we have common language. So we've been doing it verbally. We have an algebraic equation. We have a graphical representation, and we've had motion maps. And if you look at this particular slide, you're going to see that the graph, this is for constant velocity, the graph, the equation, and this thing called a motion map all say the same thing. Algebraic, graphical, diagrammatic representation. That's what modeling is all about. So it's the process in which we construct, refine, and use these conceptual models. We represent the objects and processes via these ways. Instead of having a boatload of chapters in the book that we have to go through, we have a small set of conceptual models. Why modeling? Well, we want to give students the opportunity to do science rather than just learning about it. We want to make the coherence of scientific knowledge explicit. The construction and testing of models is a central activity of research scientists, and models and modeling figure prominently in the NGSS. So we took a rapid trip through a modeling cycle. We observed, asked questions, we collected data, we developed a model. Then we tried to use it, and it worked very fine for all of the cases where the object was moving at constant velocity. But then when we looked at an object like the golf ball or the wheelie rolling down the rails, we test the model and we realized it didn't work.
Well,
So
it has boundaries, right? It
has
works
boundaries,
in
that's right.
certain circumstances only.
Yes, exactly. So we had to refine the model and make the new model for uniform acceleration, and then we run through this cycle again.
All
Okay,
models are wrong, but some models are useful. So,
some models are more useful than others, yeah, for
right,
sure.
right.
So I'm going to show you a document which you will get access to this slide set, which will allow you to do this at your leisure. The science and engineering practices are out here in blue boxes to the right. And this describes our pre-lab, our model development, pre-lab discussion, conducting the experiment, whiteboarding, where we analyze and interpret the data. We use mathematical and computational thinking. Then we report our results and communicate them. There's one of the big components of modeling instruction is student articulation of what's going on rather than doing an experiment to confirm what the teacher told them in the beginning. All right, so now I'm going to go back to our.
So while Larry's doing that, I'm just going to tell you, we are, for your amusement and edification, or your review if you like, we're putting in the chat, I'm putting in the chat right now, some links. The first one is a link to that worksheet 4 that we showed you with the velocity and position time graphs. And the next one is that graphic. And the next one after that is the the physics storyline, the physics mechanics storyline from
Haven't
the
got, yeah, I can show
website.
that real briefly, I think.
And the final one is a very brief survey that we would be so appreciative if you would complete.
So am I still showing my screen?
You are.
You see that? Okay, so here's a storyline for what we do in physics mechanics. And I do want to point out to you that after you look at this, you can go down and look at sample materials, and you can get the whole set of materials, which include the teacher notes, how to conduct the experiments, the various worksheets and stuff like that. They just don't have quizzes or tests. All right, so now I'm going to go back, and I think we're just about done. Not?
Yep, we are.
And so here we have
All our channels.
all of our channels. And should you be interested in a modeling instruction workshop, you can contact Sue at this website. And there is the sneak peek
The
survey.
survey, if you want to do it on your
You
phone.
put that
you
link
just
in the
take a
chat?
picture.
I'm sorry, Colleen, did you put that
I
link?
put the link in. I did.
Okay. Okay.
I just want to say one more thing, since we're all physics teachers here. If you teach astronomy, or even if you just teach physics, but you would like to do an astronomy themed physics course, we have the most awesome astronomy workshop. And it's a distance learning workshop. It begins in January, and there are scholarships available for anybody who wants to do this. Half tuition scholarships for the physics modeling workshop. This has only been going on for 3 years. It utilizes many of the same, all the same fundamental physics models that you see in mechanics are there, and also light, and it's yeah, everybody loves it. You should come. Okay, end of commercial.
At the very end of this slide deck are links where you can, if you want to know more about how the experiment was run or how to build the apparatus or obtaining Vernier graphical analysis, you can follow those links. Okay,
Okay,
are we done?
we are really done. We're really, really done. And thank you so much, Alan, for hanging out. We really
Yep.
appreciate you showing up. And you're a great student mode people, and I'm just going to give you a round of applause.